In this video, I want to talk about some related concepts on effect sizes, confidence, and power. So if we reject the null hypothesis, we merely indicate that an effect is not zero, or at least that we try to reject the idea that it's zero. It doesn't actually tell us how large the effect is. So not zero can mean anything. It can mean like tiny difference, or it can mean like it's actually substantial. For this reason, we have effect sizes. The effect size is something that we can calculate that measures the strength of the effect of interest. And there are many different versions of it. They're usually between 0 and 1, for example, if they're standardized, or they're just like the difference in means if they're unstandardized. And every test usually has their own effect sizes that are useful and are good to report as well. So for example, the correlation is an effect size. We use Cohen's D as a sort of standardized metric for difference between two means of two groups in the independent samples t-test. And there's some others as well. Many test statistics have associated effect sizes that can be reported alongside the test result. And you should always really try to report this. One thing that's really important, and many people don't really realize this, the p-value is not an effect size. And that's very, very important. Sure, it's probably related to it, like if you have p is 0.0001, there's probably like a pretty substantial effect. But it could also have been that your sample size is just very, very high. Like the p-value is massively impacted by the sample size. That's because the standard error becomes smaller as the sample size becomes larger. So having a very, very significant effect could just be because you had a very, very, very large sample. And in a very large sample, you can get a very significant effect for a very tiny effect. Right? So p-value you really cannot interpret. You cannot say, okay, this was 0.001, that's great, and this is 0.04. Oh, that's not that good. Right? That's not how the p-value works. That's not what it does. We just agreed that below 0.05 we deem significant. That's also kind of silly if you think about it, a bit arbitrary. You could also do 0.06, 0.07, sure, why not? But yeah, that's what we agreed on. That we would deem things below 0.05 significant. And it doesn't really tell you anything about how strong the effect is. A standard error is a measure of variability of an estimate. I already talked about standard errors before. A standard error tells me what's the variability in an estimate. Where we talked about standard errors of the mean. So that's the distribution of the mean, the width of that mean has standard error. But we can also think of this for any parameter, really. Standard errors can be used to form confidence intervals. Now, confidence interval is a region around the mean that indicates where we expect the values to occur if we do repeated measures, or where we actually expect the population value to be. We can draw, for example, a 95% confidence interval on the mean by taking interval of that mean minus 1.96 or 2, roughly 2, that's the z of 2, times standard error, and plus 1.96 times standard error. A confidence interval is a range of values that is likely to contain the true value of the parameter of interest. That's a bit of a weird way of phrasing it, but the exact interpretation is that in repeated sampling, and hey, look, repeated sampling, we're talking about a frequentist statistic, because we're talking about potentially doing something over and over and over again. In a repeated sampling, 95% of the intervals formed this way will contain the true population parameter. It's not exactly the same as saying 95% probability that the true parameter is between these two values. In a frequentist interpretation, it's either is or it is not in the confidence interval true value, and we don't know. But in 95% of the times we form it, it will contain the true parameter. Right? So it does not tell us actually the probability that true value is in the confidence interval. For that, we need something called credibility intervals, which we can compute if you're a Bayesian, but not if you're a frequentist. Last thing I want to talk about in this video is statistical power, which is an extremely important topic that you always need to mention if you start research, not after you did research, because it's really not interesting then, but it's interesting before you conduct research to see if your sample size is good enough to actually make your research feasible. Statistical power is the probability of correctly rejecting null hypothesis when it's false. So we have a null hypothesis. It's either true or it is false. The effect size is 0 or it's not. And we can either accept the null hypothesis or reject it. Yeah. Then we define a type 1 error rate, alpha. We call it type 1 error. We make a mistake, right? The null hypothesis is true, we reject it. 5% of the times we reject it. That's our alpha level that we accept. We got an error because it's like a mistake. The null hypothesis is true, we reject it. We can also make a mistake the other way around, a type 2 error, where we accept the null hypothesis or we don't reject it even though it is false. That means there is an effect, but we don't deem it significant. We call it beta. Then 1 minus beta is what we call the power. Probability that we correctly reject the null hypothesis when it is false. We don't know statistical power because we don't know the population value of the parameter of interest. We don't know actually, okay, if the mean is not 0, we don't know what it is. But we can guess, we can have a prior idea about it. We can estimate before running a study what this effect could be from similar studies that were performed. And based on that, we can use the effect size from a previous study. We can then estimate the power, but we can also say, okay, how much sample size would I need to get a power of, let's say, 0.80? You get an idea of what our sample size is that we require. That's a really strong thing to do, a really important thing to do. And if you write, for example, a grant application to do research, you always need to mention this, okay, we actually have enough power to do this. A sample size, let's say 500 people is reasonable. Maybe it isn't. That means that, okay, if I collect 500 people, the effect is so small, I don't expect that I can find it, okay? No, elements for values, this is true, okay? Yeah. So let's say we have statistics, we have an alpha region, so that means that if you're above this level here, we're going to reject the null hypothesis if we get anything in this area, even though in this case, null hypothesis is true. But there might be some true sampling distribution around some true mean that is not 0, right? In this case, we don't know it, but let's say we can estimate it. Then this area here corresponds to, well, this should be accepting. This area here corresponds to the type 2 error rate, the probability that we accept the null if the null is not true. That's from this distribution, which we don't actually really know, but we can estimate beforehand. But use this cutoff based on the null distribution. Then we see, okay, how much of this distribution lies below that cutoff. The power is the remaining part, right? So you want this to be high. Now what happens if you increase the sample size? It becomes higher, right? Larger sample size, it becomes smaller. Now the power is super large. There is not really an area left here for type 2 error. So we expect that, okay, if we conduct this research, we're going to find an effect. In a lower sample size, the power is smaller. So we expect, okay, maybe risky to conduct research if it's very costly. We might not find the effect we're interested in, and then, yeah, we don't really have anything to talk about. That's statistical power, and that's a very important topic as well. Okay, and that's it for this video series on inferential statistics.